Hello, Assalamualaikum. Today, our group will be presenting about MAT183 calculus topic application of differentiations about apply maximum and minimum. So, there's two of us will be presenting about this topic. My name is Muhammad Ishaq Ramli, student ID 2023478798. And my friend's name's Amir Haziq, student ID 2023806078. So what is differentiations? Differentiation is a mathematical process that helps us find the rate of change of a function. So the key concept to this topic is it tells us how one quantity changes with respect to another, like how distance changes with time or speed. In simple terms, it helps us identify where a function is increasing, decreasing, or stationary. So the formula of rate of function is dy over dx equal to fx equals to y. What is maximum and minimum? Maximum and minimum values are the highest and lowest points of a function within a specific range. This is how you identify some maximum and minimum. Use first derivative to find critical points. Second, use second derivative to confirm fx or x, that thing, and the minimum point and the maximum point. Why we apply maximum and minimum values? It is because the derivative of a function at a point where it reaches a maximum or minimum value will always be zero, allowing us to identify these critical points on a graph and find the exact location where a function reaches its highest or lowest values within a given interval. Maximum and minimum problems are applied in various fields to optimize results, make decisions, and solve real-world problems involving efficiency, costs, and performance. The goal is to find the optimal point where a function reaches its highest or lowest value. So one of the problem statement we'll discuss here is first, a company is designing a box with a square base and an open top that must have a volume of 500 cm square. What dimensions, length of the base and height will minimize the surface area of the box. And second, maximize the surface area of the box. So let's discuss here. So the volume given is V equal to x power of 2h, where x is the length of the base and h is the height of the box. We are told the volume is 500 cm square. So x power 2h equal to 500 and h, so we just like doing some algebra here. So h equal to 500 over x power of 2. The base area is equal to x power of 2 and the four sides area of each side equal to x, h equal 4x. So surface area equal to A equal x power of 2 plus 4x. So conclusion is x power of 2 plus 4x and 500 over x power of 2. And to minimize the surface area, we differentiate A with respect to x. So it become dA over dx equal to 2x minus 200 over x power of 2. So set to dA over dx equal to 0 to find critical points. So we become 2x minus 2000 power of x power of 2 equals 0. Multiply both sides by x power of 2 to eliminate the denominator. So it become 2x power 3 equal to 2000 and x power of 3 equal to 2000 equal x equal to 1000, sorry. When x equal to 10, substitute into the volume equation to find h. So now h equal to 500 power of x2 equal to 500 over 10 power of 2 equal to 5. Thus, the dimensions that minimize surface area are base side length equals to 10 cm, height is equal to 5 cm. The minimum surface area is A equal x power of 2 plus 2000 over x equal to 2 equals to 10 power of 2 plus 2000 over 10 equal to 100 plus 200 equals to 300 centimeter power of 2. And we maximum surface area. The maximum surface area, the surface area does not have a infinite maximum, as it increases as x approach 0 or infinity. So next, Amir will present about other problem statement.
So next up, we got another problem. The problem statement is, a farmer has 200 meters of fencing and wants to enclose a rectangular field. One side of the field is along a straight river, so no fencing is required on that side. What dimensions of the field will maximize the enclosed area and minimize the enclosed area? So the solution is, L is equals to length of the field, which is parallel to the river, and W is width of the field, which is perpendicular to the river. So given the constraint of fencing, we only need fencing for 3 sides, which is 2 sides of W, which is width, and 1 side of length. So the solve for L is L plus 2W equals to 200. So if we simplify that, we got L equals to 200 minus 2W. So the area A of the rectangular field is given by A equals to L times W. That is the formula for rectangular. So substitute L equals to 200 minus 2W that we got before into this equation. So A equals to 200 minus 2W times by W. And we simplify the equation, we got A equals to 200W minus 2W square. To maximize the area, we differentiate A with respect to W. So we got dA over dW equals to 400 minus 4W. Set dA over dW equals to 0 to find the critical points. So 200 minus 4W equals to 0. And we got W equals to 50. So we differentiate again to check concavity. And we got 2 square A over dW square equals to negative 4. So since d square A equal over dW square 2 equals to 0, this indicates that W equals to 50 corresponds to a maximum. When W equals to 50, substitute the equation for L. So we got L equals to 200 minus 2 times 50. And we got the answer 100. Thus, the dimensions that maximize the area are length equals to 100 meters and width equals to 50 meters. And the maximum area that we can get is 500 m square. And how we got that is by we use A equals to L times W. And we already know the L needs to be 100 and the width need to be 50. And we got 5,000 meters square. So to minimize the area, consider the extreme cases where either W or L approaches 0. So if W approaches 0, then L equals to 200 minus 2 times times 0 equals to 200. And the area A equals to 200 times 0 equals to 0. If L approaches 0, then W approaches 100, and the area is A equals to 0 times 100, and we get the answer 0. Thus, the minimum area is 0, achieved when either the length or the width is 0. So, the first step is to break apart the problem, understand what's being asked, and write down the key formulas or relationships, and then pick a strategy to solve. In this case, we use differentiation to find the maximum value and the minimum value of the area function. And then the last one is to solve and label. Find the answer. So the conclusion is, differentiation is a fundamental mathematical tool with wide-ranging real-world applications. It enables us to analyze and optimize situations involving rates of change, such as determining maximum or minimum values in problems like optimizing costs, maximizing areas, and minimizing surface areas. Additionally, differentiation helps us study the behavior of functions, including intervals of increase or decrease, concavity, and points of inflections. Its applications extend across various fields, including economics, engineering, physics, and business, where it is used to model and solve complex problems effectively. So, these are the references that we got from the website. And that's all from us. Thank you.